Hello everyone. So we're going to talk about Project 4. Project 4 has 3 parts to it listed there. So Part A is MST, and everything that you need to know about that is in the MST lecture. Part C, the optimal TSP, comes from the backtracking branch and bound TSP lecture. And Part B is somewhat related to Part C, but you're going to have to do some of your own research. We'll talk about that a little bit later on. You want to do these in order, A, B, C. And that's because Parts A and B are going to be used later on in Part C. When you're looking at your autograder feedback for this project, for every part of the project, watch the autograder output for the word hint. So search it through there. There's some really good hints on some test cases with things that students commonly do wrong. When you're looking at your output of this, one thing that's both good and bad, perhaps, is that for every part, your output could be different than ours and still be correct. And so there's a program on the autograder called The Judge that judges your output, and there's a different judge for each part. So for example, in Part A, if I had something like 4 vertices, well, if I do an MST of this, and let's say that the distances here are all 1, there could be several different MSTs. I could have an MST like this, MST like this, MST like that, MST like that. So there's 4 different sets of edges I could choose, and for any one of them, there's 3 different orders that I could list the edges in. So you could have one of 24 different answers and still be correct. So the judge basically says, does your total of the edges match our total? If so, that's good. If not, it must be wrong. If your total matches ours, then let's take the edges that you listed and add them up. Do they add up to the 3.00 that you said your cost was? If those add up, that's good. If it doesn't, then you've got something wrong. You reported the right total, but the edges don't match that total. And then we also check to make sure that it makes sense. So for Part A, we determine, does it actually form an MST? For Part B and C, we check, does it actually form a cycle? So, like I said, it's good that you can put them into different order, but sometimes it can be a little bit problematic for debugging if they're listed in a different order. So, really, sometimes you have to just submit this one to the autograder and get the feedback and see if you're right. There is, however, a tool that we provided, and it's called the visualizer. Actually, it's listed as visualization tool. So search for the word visualization in the project spec, and there's a link to Autograder 2. The tool only exists on Autograder 2, but what it allows you to do is to select an input file and an output file from your computer. Then you select the mode, either MST or TSP, and hit the button, and it will show you what your output looks like. So given this input and these edges, it'll show what your MST looks like. So that can help sometimes. Sometimes with a bigger output, it might make it more confusing, but with a smaller one, it'll show you some useful things, and it'll allow you to determine what's going on there. We're also going to have some help later for debugging Part C, so specific information there. One other thing to be careful of, in any part of this project, you have to be careful if you're running a big input inside of your IDE, because by default your IDE is a debug build and that could be run slower. In Part C, it doesn't have to be that many vertices for Part C to be big, because Part C, the TSP, optimal TSP is O of V factorial. And so it doesn't take a very large V to produce a really big V factorial. So even like 10 or 11 vertices might take 20 seconds to run inside of your IDE. So be careful on trying to judge, oh my God, it's taking forever in your IDE because it's running slower due to the debug build. Okay, now in part A, so the project is Zookeeper, and so we've got to plan out some routes between different displays in our zoo that people are going to visit. And one thing about part A is that there are 3 regions to the graph. There's the region, let's say here, which would be in geometry terms quadrants 1, 2, and 4. So quadrants 1, 2, and 4 are the normal cages, or you could call them the safe cages. The ones down here in the bottom left, or quadrant 3, that's the wild animal cages. And what's shown in blue is the border between the safe cages and the wild cages. And when someone is touring and going from one display to the next, we don't want them to enter the wild animal area without knowing it. So there might be, say, some places up here in the safe area, and there might be one down in the wild, and there might be, say, there's got to be at least one of them on the border somewhere. There might be more than one. There might be 2 border locations. There might be 3. But you cannot go from, let's label these points, like if I say, hey, I'd like to go from A to B, you should disallow that from happening in part A. In parts B and C, you don't have to worry about this. Now, you might want to say, hey, let's start making, I don't need a vector of inputs, I need 3 vectors. I need a vector for the safe ones, a vector for the wild ones, a vector for the border locations. Too complicated. Put them all in one vector. You could save some time later and categorize them as you read them in, so you could remember the XY coordinates and a category. Safe, wild, border. Could be a char, could be an enum. Don't make it a string. And then you could categorize them as you read them in. And then later on, when you're doing your MST, and we'll talk about which MST to use in a minute, when you're doing your MST algorithm shouldn't know about wild and safe and border. Because I've seen people try to do things like, I'll make an MST of all the safe ones, I'll make an MST of the wild ones, and then I just have to connect them with 2 edges. Well, that might not be the shortest way to do it. Maybe the shortest way to do it in this one would be to go like this and like this. If I draw it a little bit more careful, it would be obvious that the best way to connect A is to that one. So let's change that just a little bit. Do that and that and that. Okay, so if A was over here, hey, well then the best way to connect A is to go to that one. And then, maybe the best way to connect these together is that. And then maybe this one will go here and that one will go there. So you can't just say, let's connect the outer and let's connect the inner and connect them. That would be disallow good solutions. So think of it as your MST code and your distance helper. Your distance helper computes distances and does it with respect to the areas. So if I say, hey, what's the distance from A to D? It might say 18.3. Okay, what about the distance from D to E? 9.7. Okay, what about the distance from E to B? Well, the edge doesn't exist. So if the edge doesn't exist, infinity. And then your MST algorithm will choose something better than infinity. So we don't want to have the MST algorithm worried about it. Just call a helper, function, functor, whatever you do. Call the helper says if it's wild and safe or safe and wild, it says infinity, otherwise it gives you a number. And then the MST will make use of that number in the best way. And it won't end up connecting things with an infinite cost. When you categorize them, don't make your categorization too simple. I've seen people do their categorization and have more things coming up as border than there should be. You also have to be, in this project, you have to be careful when you compute a distance, you've got to be careful with integer overflow. Because our program that generates these basically generates random numbers. And the more XY coordinates we told it to generate, the farther out it spread them so that we wouldn't get too many on top of each other. So let's say I had an X coordinate. So I've got like X1 minus X2, right? I'm trying to do like X1 minus X2 times X1 minus X2. I'm trying to do like X squared, difference in X squared. Let's say that these are 25K and minus negative 25K. If you do these as integers, this is 50,000. 50,000 times 50,000 is negative 500 million approximately. So you've got to be careful with your multiplication. Get things to a double. Also, do actually do multiplication. Don't do POW, 2.0 because the POW function is slower than multiplication. When you want a square root, use SQRT. You really don't want to use the POW function at all in this project. It's very general purpose, so it's slower than very specific things like multiplication and square root. Now, when we print our output for part A, our output actually lists the edges in the order that we selected them. And so that can make your debugging easier. It could make comparing them harder, but if you were to, say, temporarily add some debugging output to print the edges in the order that you selected them, instead of after you were done, you got to print the total distance followed by the edges. If instead you temporarily print the edges as you choose to keep them, then you would have them in the same order as ours. So that could make debugging easier for part A. Now let's go back to what MST should we be thinking of this as? What we really need to know is this graph dense or is this graph sparse? All right, well, what if I had a graph like this? If I had something, I'm just going to draw the axes in one color so I don't do too much there. Let's say everything was in the safe animal area. It's a petting zoo. It's completely connected. Well, what if all of the cages were in the wild animal area? We got a wild animal safari. That's completely connected. What if it was something like this? What if we had, I'm trying to get rid of a bunch of these. What if I had something like this? I've got one wild one, and if I've got one wild one, I've got to have one, I'm going to make it green here, I've got to have at least one on the border. So if I've got normal, or let's say safe, if I've got safe and wild, there's got to be at least one border. We will not give you an input that is not possible to solve the MST. You might want to check for thinking that it's impossible, just so that you know whether your own input files are valid or not. And the autograder, if you give us an invalid input file, it will tell you, but you don't have to check this. The autograder won't do it to you. So, question is, if there's only one safe, or there's only one wild, how dense is this graph? Well, everything here is completely connected, including the border. This one's connected to that one. Basically, the only edges I'm missing are the ones that go from a wild to a safe. Those don't exist. That means there's like n minus 2 edges are missing. Well, that's still really close to n squared. All right, what if, let's draw a new graph over here. What if I had something like this? I've got basically half of them out in the safe area, half of them in the wild area, and one border. Well, this region is completely connected. This region is completely connected. Everybody in the wild is connected to the border. Everybody in the safe is connected to the border. The only things we're missing are the ones that go from wild to safe. Still looking fairly dense. So if it's always going to be dense, then we should be creating a nested loop prim solution. We don't want priority queue prim. We don't want Kruskal. They would take too long because of the density of the graph and the complexity of the algorithms. Also, if I've got, let's say, 50,000 vertices, can I afford to have a adjacency matrix or a distance matrix? 50,000 squared is 2.5 billion. At 8 bytes each for a double, that's a 20 gigabyte distance matrix. Can't afford it. So you need to determine, does an edge from like A to B exist by their categories? Safe and wild, wild and safe? No, no edge. But anything else does have an edge. And we do that by calculating the distance. And remember, this is only part A. Part B and C, we don't have to worry about wild, safe, etc. Okay, so let's move on to, we'll talk about part B first. So part B is basically saying, hey, you know, part C, that optimal TSP, that V factorial, O of V factorial, that's really a long time. We can't afford to do that for very big graphs without some really creative ways to do it. So like an army of computers, each of them running a piece of the problem, and how do we do that? I don't know. So let's not do that. So for part C, we're going to have to severely restrict our number of vertices. But for part B, we don't want to do that. Part B, what you want to do is do some searching for something called TSP heuristics. So heuristics, you can think of a heuristic as a sort of simplified algorithm. It's not the optimal one, but it will give you a decent solution much, much faster. It could always get lucky and be optimal, but it's not likely. And the bigger the graph, the less likely it is. So, you know, if I give you the 4 points in a square, most TSP heuristics better say, oh, you should go around the outside. They'd be unlikely to say, oh, you should go like this and cross the middle twice. Heuristics are unlikely to do that. But with a bigger graph, it gets harder to get the optimal answer. Now, when you look at the TSP heuristics, you want to stick to things that are O of V squared. Don't go beyond that. Because then as V gets bigger, you know, 50,000 squared, that's pretty big, but 50,000 cubed, that's getting crazy. So that would be undoable. So we want to stick to any heuristic that's O of V squared. The other thing about the heuristics, don't be afraid to try more than one. So the simplest heuristic is called, a software update tonight, fine, do it later. Okay, so the simplest one, and all of the TSP heuristics are going to be greedy. They're going to be greedy in some way or another. So the simplest one is called greedy nearest neighbor. Greedy nearest neighbor basically says, pick a starting point. How do we pick a starting point? Turns out B and C have a requirement. You must start at vertex 0. So the vertices names are the order you read them in from the input file. So wherever it is, vertex 0 is the first one you read in. So you've got to start your cycle at vertex 0. Greedy nearest neighbor says, pick the closest one to where you are, okay? I picked the closest one to there. Now, this is where I am, pick the closest one to there. All right, so now I'm starting to make a cycle that looks like that. Pick the nearest one to where you are. Okay, I'll pick this one. Then let's say that was all of my vertices. I picked the closest, the closest, the closest. Now I've got to close the cycle, go back across the middle. Oh, That's not optimal. So greedy nearest neighbor works, it's easy to code, but it's more likely to produce a graph that is further away from optimal. So how do we fix that? Two different ways. One of them, like I said, be willing to try a different heuristic. The other one is you follow greedy nearest neighbor with something called 2opt. And 2opt is in the Project 4 tutorial PDF that's in the Canvas folder. So that one's got some stuff about different parts. It's got some stuff about calculations, like I think it's got the hint about the integer overflow that I already mentioned. But it's also got a demonstration of how 2opt works. So your choices are add 2opt and make sure, again, if you do 2opt, it's got to be O of V squared. If you look up 2opt, many sources of 2opt will show you a V cubed way to do it, and that's too long. So you've got to do it in V squared. So look at the tutorial; it'll talk about it. And also, you can come to office hours too. There's a bunch of other heuristics. There's Christophides, I think, is kind of hard to implement. There's a set of 3 heuristics that all work pretty well. They're called insertion heuristics, and they all work in similar ways. They pick the next vertex in a very different way, and then they insert it in the same way. If you're doing any of the insertion heuristics, what you want to do is you want to keep, and really, I should go back to this. For Part B and Part C, your path should be a vector of indices. And a lot of students are going to want to say, well, I'll just make a vector of coordinates. Well, vectors of coordinates are bigger. It's longer to shuffle them around in Part C. It's longer to copy them in Part B. And also then you'll find, because what you have to print is indices, then you'll go, oh, wait, I got to go add more data to a coordinate so I know which index it is. Just keep a vertex of indices. So when you're doing Part B, if you're doing an insertion heuristic, start out with your path being 0, 0. Because then, however you pick the next one, you've got a place to insert it. And it'll make the code a little bit easier to consider all the points to do the insertion if you have an extra copy of 0. Now, it'll also get easier to get the right answer also, but before you print, you'd have to, like if I end up with the path like 0, 5, 2, 1, 3, 4, 0, I would want to do a pop back before I print things because I don't want an extra 0 in my printing. There's also a link in the project spec to a demo that I recorded a few semesters ago of running in MATLAB. It actually visually shows you greedy nearest neighbor in action and 2opt shortening its path. So if you want to, you can look at that video also, but you don't have to. Okay, so let's talk about Part C. So Part C, important thing in Part C is make a class. Even if Part A doesn't have a class, Part B doesn't have a class, still okay. Part C better have a class. And the reason is we gave you a function in Part C called genperms. And it's in the lecture slides. There's also a version of it on Canvas in a text file that you can just copy and paste from the text file because the PDFs aren't safe to copy and paste from. So we've given you genperms, and genperms, as we gave it to you, it has 2 parameters. To actually turn our sort of starting point genperms into fully functioning genperms has to know more things. And if you don't make a class, you'll have to keep adding parameters to genperms. Well, genperms is a recursive function that's not tail recursive. And that means every time it calls itself, whatever's in parentheses has to be pushed onto the stack. So if you're pushing 7 things onto the stack, v factorial times, that's a lot of time spent pushing and popping. So instead what you want to do is you want to take the genperms that we gave you that had 2 parameters and get it down to 1. You want perm length to be the only parameter. it's possible to get it down to 0 and make permalength a member variable instead of a parameter. It's a little harder to do. The others are easier to make member variables. So you'll end up adding a bunch of member variables to your class. Well, what will you have? You'll have your coordinates that you read in. You'll have your path that you're building up. You'll have the best path you've ever seen, the length of the best path you've ever seen, the length of the path you're working on. So at least, we gotta have at least 5 member variables there. The thing I mentioned of the current path length being a variable, that's sort of like a running total. Like, as I'm doing part C, basically what I'm doing is I'm saying, hey, I've got a vector. Let's see, oh, wait a minute, let's talk about calling genperms. So genperms, if perm length is the only variable, what you've got to give it, you've got to have a path. So the path has to have in it 0 and then everything else. And the very first call, perm length, has to be 1. And what perm length is telling you is how many vertices in the path are fixed or permanent, how many of them are still allowed to be changed and reordered. So when we say perm length is 1, that means 0 is fixed, don't move it. And that's important because if you went from 0 to other things and back to 0, well, that's the same as going from vertex 1 to other things and back to 1, which is the same as going from vertex 7, all the other ones back to 7. They're all the same path. If you consider every starting point, it's v factorial. If you only use 0 as a starting point, we're down to v minus 1 factorial. Still terrible, but if v is 35, we're 35 times faster than v factorial. That's a big difference. Okay, so when we call genperms, we got to give it perm length of 1, and the path has to have 0 followed by everything else. The order doesn't matter in terms of getting the right answer. The order could matter in terms of getting that answer faster. So think about that. What would be a good order for things in this path so that you can get the answer a little bit faster? And the way it would get faster is genperms, the basic idea is we've got to run through every permutation of these things. And anytime we get a total cost and we get to a leaf node, we get to the base case. Aha, genperms has a base case because it's a recursive function. When we get to the base case of genperms, that's when we say, hey, is this total cycle length that I've got better than the best one I've ever seen? If it is, update the best I've ever seen. Both variables, the best path length and the best path, set them equal to the current path and the current cycle length. So the sooner that gets smaller, the more pruning we do, the faster we run. So that's what I'm getting at here, is we want an order here that will hopefully give us that reduction in path length sooner than another order. So you got to think about that. Let's see, where am I? Okay, so how do we keep a running total? I mentioned the current path length should be a running total. If you look at genperms, and if you don't have it up already, pause the video, bring up the genperms code and take a look at it. Let me see if I can. I'm pretty sure I've got mine handy. What I want to do now is get my software to share it with you. Ooh. I don't have an easy way set up to do that. I should have done. Okay, I can do this. It might look a little weird because I'll just put that in front of it. Alright, so I'm just going to show my whole desktop here for a minute. We're going to get infinite recursion until I switch over to the genperms. Okay, here we go. So, in genperms, so this is the base version of it, simple version of it. So, here's the base case. If perm length is equal to path.size, that means we've reached a leaf node. We've Everything has been fixed. Nothing can be reordered. We're in the base case. And the do something here is the, hey, let's get the total path length, see if it's better than the best so far. If it is, update the best so far, and return. We got to return. We're a base case. Okay. If we're not a base case, we've got to check if it's still promising. We'll talk about that in a bit. If it's not promising, we go back and we make a different choice. And here's the guts of GenPerms. This is the part that runs through every possible permutation. So it says basically swap something, basically pick someone new to be part of the path. And here's an interpretation down at the bottom. So when the path, let's say my path had A, B, C, D, E, F, G in it, and perm length is 2. What that means is that A and B is fixed, and C, D, E, F, G can be permuted. If the swap happens to put C here, and we make a recursive call with perm length 1, so now I'm here. It's still the same path, but perm length being 3 means A, B, and C are fixed. D, E, F, G still can be permuted. Now, think about this. Right here before the recursive call, I could say current cost plus equals the cost of the new edge. In our example, what edge is that? I'll let you think about it for a second. We used to say AB was fixed. It used to be current cost was AB edge. Now current cost should be AB plus BC. Well, we can't write the code in terms of B and C. It's got to be written in terms of what is the index of these things in the path vector. Think about using perm length to help you with the index. So then I make a recursive call where ABC is fixed. And when that recursive call is done, think of it in terms of preconditions, postconditions. Before the recursive call, there was only one edge in the total cost, or current cost. After the recursive call, I've got to subtract it. Current cost minus equals the cost of that same edge. That's how I get a running total. And where we put them is important with respect to the swap. I could put it before or after, but the code would change. It's easier if you put it right before the recursive call and right after, because then the indices of the edge will be the same. If you move them around, it would be in different places. Other thing we have to do, when we get down here, we haven't finished the whole cost. Let's say if I did this, if I had, I'm going to copy this here. If I had this with a 7, that means that A, B, D, let's say A, B, D, C, E, F, G is fixed. But every time we added an edge, we added something like this. We added the cost of a new edge like this one. Or we added the cost of the BD edge, or we added the cost of DC, CE, EF, FG. We've never added the cost to close the cycle. We got to do that up here. We got to do the current cost plus equals the closing edge. We got to check if it's better, update things, and then before we return, we got to undo whatever we did. We got to have preconditions, postconditions. Before the base case, or before I checked if it was better, I had a certain cost. After I'm done checking if it's better, I better have the same cost, because I'm going to roll things back. When you get done with GenPerms, path is meaningless. Current cost should be 0 or really close to it. This is why you need, when we say update things, this is where the best path I've ever seen and the best cost I've ever seen are super important. They get changed in the base case. When GenPerms is done and we're back to main or whoever called GenPerms, we don't look at path and current cost, we look at best path and best cost, because those are the ones that got changed until they were the best. Then path gets changed all the time. Path is always changing. but current cost, because everything we add to it we subtract. If current cost starts out at 0, when GenPerms is done, current cost better be either 0 or really close to it. Like if I had a current cost of like 1 times 10 to the negative 14th, that's still 0. That's accumulated round off error, not a big deal. Okay. All right, so when we are looking at doing MST, doing OptSP, why do we want to call A and B? Well, let's start with why do we want part B from OptSP? If I haven't done any permuting yet, what's the best cost I've ever seen? I could say, hey, my best cost I've ever seen is infinity. Well, the problem with infinity is that everything looks better than infinity. And one of the goals of promising is to prune things that look like they might not be better. So promising in general has 2 goals. Let's roll that back a second. Promising has to tell you, should you continue or not? Promising true means yes, you should continue. Promising false says no, you should go back and change your mind about something. If we're talking backtracking, promising has one job. If you violated constraints, it's not promising. Now, in branch and bound, promising has 2 jobs. If you violated constraints, you're not promising. And if you don't look like you're going to be an improvement, you're not promising. However, in our part C, there's no constraints to violate. We're going to try every possible permutation. Remember, no wild, no safe, no nothing like that. So really, our promising only has one job. Has to answer the question, do you look like you will be an improvement? If you don't look that way, you're not a good beginning. We should go back and try some different path. So, if we start off with a best cost of infinity, everything looks better than infinity. I could start with a graph, and here's where promising comes in. Let's say I had a graph like this. Okay, and let's say these are vertices are A, B, C, D, E, F, G, H, I, J. Now really in your project they would be 0, 1, 2, 3, 4, 5, 6, 7, etc. Now let's say I go with my first possible permutation. My first possible permutation, and let's say distance here is 1, every one of the vertical distances is 1, and this is a distance of 10. Would you say, as a human, this looks like a good beginning for a TSP? No, that doesn't look good. But we need to capture that somehow inside of a program. If I told you the best cost was infinity, you'd say, wow, this is looking way better than infinity. Let's keep going. But let's say I told you that the best cost so far was not infinity. Let's say the best cost so far was, let's say it was 35. Well, then how do I determine if this looks better? Well, I could add up just what's there. So this is 10, let's say this is 10, 11 approximately, and another 10, that's 31. That still looks okay, but that looks bad because now I'm up to like 42. So that looks worse. But what if I could say this doesn't look good even sooner? What if back here, oops, I erased one too many blue lines. Let's say that back here I could say, hey, this doesn't look good. Well, how would I do that? The 21 isn't sufficient. What I would need is I would have to have a way to estimate how long do you think it would finish me to cost me to finish the path that starts ABC. So this gets into 2 things. First of all, how do I get a best cost better than infinity? Well, I could call part B. Part B might get lucky. It might be optimal, in which case part B can do lots of pruning because nothing looks better than the perfect solution. Even if part B doesn't get lucky and get the perfect solution, it'll be closer than infinity and we'll be able to prune more. So that's why we want to call part B. And when you call part B, it's important to remember both things that part B tells you. Not just the cost, but the path of part B. If part B gets the lucky perfect answer, then part C can never improve upon it, and you got to print something. You don't want to be the person that ends up with the right answer for the path length, and the best path is an empty vector. So after you call part B's cost is your best cost, part B's path is your best path that you've ever seen. Okay, so that's our starting point. Now, how do we get that? Does this look like a good beginning? So now I'm going to go to a different example that's from the lecture slides that's a little bit easier to see. Okay, so I've got a couple parts here. So I've got that part, and I've got some in the lecture slides. They're gray. I think the green might be a little bit legible. Let's see. So yeah, a little bit legible, not great, not terrible. I'll make the dots a little bit bigger. So I've got what I've got in the video, in the lecture slides and in the video is I've got vertex A, vertex B, vertex C, and this right now my path is A, B, C. How do I know that? Because path actually contains A, B, C, and some other stuff, but my perm length is 3. That means these 3 are fixed. The other things, the D, E, F, G, are still mutable. So this is down here. This is my D, E, F, G. So I want to know, does this look like a good beginning? Well, visually, yeah, that looks like a good beginning. But what if B was actually, instead of being up there, what if B was down here? Would you say that, let's make it red. If B was down here, would you say that A to B to C is a good beginning for this? No, you wouldn't. But we need to get a handle on how do we do that. So here's the observation. I need a way to estimate the cost of finishing this thing, but it better be shorter than the factorial of finishing it. So I want to do less work than factorial. If I just finish the factorial, that's factorial work. I want to get an estimate faster than that. So, observation. If the path starts out ABC, then there has to be some edges that go from C down to here. It's got to go to someone down there, and I've got to get back to A. So those 2 blue edges, somebody's got to connect to the end of the path, somebody's got to connect to the beginning of the path. And it's got to be somebody in the unvisited section, the not permanent section. So it's got to go ABC, something, 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 goes back to A. So those 2 blue edges, Professor Darden calls them the connecting arms, those blue edges need to be calculated. Well, that's not too bad. What's my best starting edge? Infinity. What's my best ending edge? Infinity. Let's loop through the unvisited ones. Hey, distance from D to A, are you better than the best I've got? Yeah. What about D to C? Are you better than the best ending? Yeah. Okay, I update my best ending distance. I don't care who I connect it to. I just want the shortest way to connect it. Then we need to connect. So I went A, B, C, goes down to the unvisited connect to each other, and then they go back to A. Well, that means the unvisited have to be connected to each other. And we've got to, here's a key, we've got to always make a choice here that is less than or equal to reality. If I make a choice that's bigger than what optimal might pick, then I might prune away the best solution. For example, if I said, hey, A to B to C is a cost of 7, what do you think the cost of finishing this is? And my estimator says $1 million. I go, oh my gosh, I've got a 37 solution. $1 million and 7 is way worse. Let's prune it. So obvious exaggeration to say $1 million, but if it's over the optimal, I could prune. And I don't want to prune away the optimal. So my estimate must be less than or equal to reality. Well, the edge from C to whoever's closest unvisited, it can't be shorter than that. There's got to be an edge like that. The edge from the closest unvisited to A, take the shortest one, that's got to be optimal. There's no way to do it shorter. But the other thing we've got to do is we've got to connect the unvisited to each other, and it's got to be the best possible way to do it, because anything worse might be wrong. It might be an overestimate. So I've got to connect D, E, F, G to each other, and I've got to do it in the smallest way possible. Sounds like MST. So if we can do the MST of the unvisited, which might look something like that, I do the MST of the unvisited. You say, wait a minute, that doesn't look like a cycle. That's okay. I don't care about what it looks like. I care what's the total cost. Right now, I've got a total cost of the black portion, and that's a real number. That's my current cost. So let's say I've got a current cost of 7. I've got my blue arms are like 5.3 and 4.8. Okay, so I've got 7 plus 5.3 plus 4.8, and then I've got the green estimate is, let's say 12.3. Okay, so I got 7 plus 12.3 plus 5.3 plus 4.8. We add this all up. 4109. Looks like a 29.4. Hopefully I did that math well and didn't embarrass myself. So let's say that my best cost so far was, let's say, 32.1. Promising would say, yeah, this looks like it could be better. It might be an underestimate, it might not be better, but I've got to keep going. This looks promising because this is less than my best so far. Promising should say true. So this is the hard part of Part C, is getting that estimate. Getting the blue edges right, getting the green edges, or in the video, or in the lecture video, they're gray edges, but I don't have a gray button on my iPad. So the gray ones, the blue ones, plus the black ones is what gives you the estimate. And it's important to get those values right. So that's why Part C is going to use both Part B as its best so far. We're going to call Part B once and we're done. You say, well, wait a minute, isn't Part B going to do a lot of work to do that fast TSP? It's V squared. We're about to embark on a V minus 1 factorial journey. Spending a little time doing a V squared to get a best cost that's better than infinity, totally worth it. All right? So we call Part B once, but then every time we call promising, wait a minute, almost every time we call promising, we want to do an estimate. Why would we not want to always do the estimate in promising? Okay, we got to look at table here. So what I'm going to look at is, let's say I said that the number of unvisited was equal to k. And k is actually equal to the path.size minus perm length. So if I've got 10 vertices and 3 of them are fixed, that means 7 of them can still be changed. All right, so I've got k here, and I've got my cost to finish my op TSP. So my cost to finish my op TSP is k factorial. That's if promising says true, I've got to do this much work. And then there's the cost to calculate the estimate. The cost to calculate the estimate, well, the MST is k squared, because MST is number of vertices squared. We're going to do the MST of just the 7 unvisited, plus I got to find those connecting arms, 2k. All right, so let's look at the top end of the graph, 1, 2, 3. Let's look at the bottom of this, not graph, table. Let's look at the bottom of the table first. When k is 10, op TSP would be around 3.6 million. But the cost of the estimate is 120. So doing the estimate doesn't add that much work. But if I do the estimate and promising says false, I've done 120 work to save $3.6 million. If promising says true, it looked good, gotta keep going, I haven't added much work. This is a win to calculate the estimate. Now let's look at the other end of the scale when k is small. Finishing op TSP, there's only one thing left to do, but the estimate would cost me 3. 2 factorial is 2, but this is 8. 3 factorial is 6, but this is 15. If k is 4, this is 24. Hey, so is this. So I could do 24 work to either not do 24 or do another 24. So this looks like a no, a no, a no, a no. How about 5? This would be 120. This would be 35. 6 would be 720 and 48. These are starting to look like wins. What this means is that when the unvisited is small enough, promising should just say true. I'm not going to calculate anything. I'm just going to tell you it looks good. And just this one if can make a big difference. Now remember, promising is going to be called v factorial times. We wouldn't want to put an if here if it wasn't going to pay off. It's going to pay off because of things like this and even things like this. So it'll pay for itself by avoiding lots of permutations or avoiding lots of estimates when we're down to just the last couple of vertices to permute. We're better off just finishing the TSP. And the way we finish TSP is have promising tell us true. Okay, now let's say that you're having trouble with part C. So one thing you can do is throw it into the visualizer to get some help. There's also, when you get the sample file, in the tarball there's a README in the sample file. Very important to read the README. It'll tell you which test cases are good for which situations. So I'm not going to repeat that. You can read it. So you could throw it into the visualizer. You can take the advice that's in the README, that's in the P4 starter or sample files. The other thing you can do is start thinking about like this. Let's say the autograder tells you that your part C is never wrong, but it's taking way too much time. What that tells me is you're not pruning enough. If, let's say, the autograder tells you, hey, you never go over time, but you get the wrong answer sometimes, that tells me you're over pruning. You're pruning away the optimal solution when you shouldn't be. What if the autograder tells you, this one's right but took too long, this one's wrong but super fast? Then you're doing both. Sometimes you over prune, sometimes you under prune. Now, if your pruning is going wrong, remember the pruning is based on the estimate. So we've got to say, hey, what's my current cost? That's the black part, plus the connecting edges, that's the blue part. That's the connecting arms. Plus the gray part, which is the MST. If that is less than the best so far, promising says true, otherwise it says false. So if you're over or under pruning, it has to be one of 4 people's faults. Either your best so far is wrong, that's pretty easy to verify. Your current cost is wrong, verifiable. Your connecting arms are wrong, or your MST is wrong. Somebody's wrong if you're not pruning correctly. All right, so what you want to do if you have to fix part C is add a C out statement. And also get rid of this check because we might want to see these also. So we might want to do the promising even when it's kind of small. So we might still want to do that. But what we want to do is we want to print out all on one line. We want to print out the current cost. That's the black. We want to print out, so we want to print out the current cost. I want to print out the MST weight. I want to print out blue 1 and blue 2, don't print the total, print each of the blue connecting arms separately, print out the total, just so you can see them all added up together. And if you use set width with this, if you use set width between these, you do like set width of 10, less than, so if you put this in between there, it'll make it line up in columns. And this will produce a lot of output. It is going to be spammy. Oh, and we want one more thing. We want, basically we want the either K or the perm length. Let's say we do K here. So let's print K also. So K tells us how many unvisited there are. Now what we want to do is we want to look for trends or things that look wrong. I've had students say, oh my gosh, Dr. Paoletti, I've been trying to debug this for 4 days. Did you do this? No, I haven't tried that. I've been looking at my code. Why don't you do that and come back to me in a few minutes? They come back to me, they go, oh my gosh, one of my connecting arms is always 0. Well, that's a problem. Let's fix it. So if you're having either too long on part C or wrong answers on part C or both, do this. So if one of your connecting arms is always 0, that's a problem. If your connecting arms always go down, they never ever increase, that's a problem. If your MST cost always goes down and never ever increases, that's a problem. Because what we should see as the number of unvisited goes up, the cost of the MST should also tend to go up. It's not strictly one-to-one, but it should be a general trend. The more unvisited there are, the bigger the MST should be. The more unvisited there are, the smaller the current cost should be. The blue arms should tend to go up and down. They will tend a little bit towards, hey, if I've got like, if I just happen to have like 2 vertices here and 5 here, maybe those connecting arms are larger than when I've got like 3 and 4, but these should still go up and down a fair bit. So look for things like that just don't make sense. The biggest problem most people have is the MST. Surprisingly enough, you'll say, wait, why? How can I get the MST wrong? You say, hey, my part A gets all the points. I've done a lot of testing. My part A is perfect. Well, maybe your problem is your handoff from part C to MST. So one problem is, first of all, we've got to make a different version of MST because we got to calculate cost differently. We can't worry about wild and safe anymore when we do the MST because that would be an overestimate. Or it might even be impossible in part C. Maybe I've got, I've taken up all of the safe or most of the safe and all of the border, and I've got a wild and a safe left to connect. The MST would say that's impossible. Okay, so you got to make sure that you're using an MST that doesn't worry about wild versus safe. Now, let's talk good way versus the way most people do it. Good way is to make part A templated and give it a functor. Part A gives MST a functor that worries about wild or safe. Part C calls MST with a functor that doesn't worry about wild versus safe. That's a great way to do it, but most people won't do it that way. What most people do is they'll say, hey, let's copy my MST code from part A and let's modify it. Okay, now my MST calls a different function to help it calculate distance. Okay, but we also got to say, hey, now my part C MST can't do the MST of all of them. So let's do an example. Let's say my path, and let's use real numbers here. Let's say my path is 0, 4, 1, 6, 3, 2, 5. Okay, and my perm length is, let's say, 2. You have to calculate the MST of those 5 vertices. Ways you could go wrong. You could calculate the MST of vertices 0, 1, 2, 3, 4, or you could calculate the MST of 2, 3, 4, 5, 6. Or you could calculate the MST of 0, 4, 1, 6, 3. Or you could have a prims table stick around between MST calls and not set things back to false infinity. So you could be doing the MST of the wrong vertices, you could be having an MST that is always shrinking because you never reset the prims table to false infinity, you might be doing both wrong. So you got to be really careful here. If you're going to say, my MST has to know all the vertices, if you're going to have to say my MST knows all the vertices, then you're going to have to do something like coordinate square brackets path square brackets I. You're going to have to double subscript, because if I is an index into the path, I don't want to say look at 5, I want to say look at the one at index 5 of the path. So you've got to be really careful here in thinking about, like, when I say index, is this an index into the coordinates, or is it an index into the path? I think of it as absolute or relative. If it's an index into the vertices array, that's an absolute index. It never changes. But if it's an index into the path vector, then it's a relative index. It's an index into the path, which is an index into the vector of coordinates. So you got to be really, really careful with the code there. Another thing you can do is, if you believe that your MST cost is wrong, here's something you can do. You could say, hey, don't just print out this stuff. Let's find a place where I know something has to go wrong. So for example, let's say it's one of the sample files and you know the right answer. So you know the best answer is like, I'm just going to look it up real fast here so that I can give some real numbers. Okay, so in the samples folder, I'm going to look at sample-E. Okay, so for sample E, we know the best cost is 328.77, and the path is 0, 9, 7, 8, 4, 3, 10, 5, 2, 1, 6. Okay, and let's say you get an answer that's different from that. You don't get that one. Like let's say maybe you get part of it. You get like 0, 9, 7, and then it goes off. Well, you know you considered 0, 9, 7. You were right up to that point. You know you at some point you must have considered 0, 9, 8, 7. And you must have said something wrong. So what you could do is you could add some code in temporarily to say, hey, if the path contains, if like perm length is 4 and path contains 9, 7, and 8 in those, because we know 0 is always there. So if these three indices are 9, 7, 8, then do some extra outputting. And what I'm going to output is I'm going to output my MST estimate, and I'm going to print out. So for my MST estimate, what I'm going to print out is I'm going to print out the total cost of my MST. So let's say my MST was like 203.45. I'm also going to print out the number of vertices in the MST, which would be, let's say, 1, 2, 3, 4, 5, 6, 7. Yeah, 7. And then what I would do is I would print out the X's and Y's of these 7 vertices. Well, hey, what you can do is you can copy and paste this into a file, run it through -m-mst, and check. If this one says, hey, the right answer here is like 159.21, you say, hey, that doesn't match. This is where I got a wrong answer, and you can do some more debugging. It's important that you do this with sample E. Sample E is all in the safe zone. Therefore, MST will give you the right total because it doesn't have to worry about wild safe. If you do this with a sample that has things in the wild animal area, MST might say infinity, or it might give you a number that's bigger than it should be because it's worrying about wild safe. Okay, so there's some debugging help. Let me go back to my list of things to cover. Yep, I think I got everything. Okay, so good luck with the project, everyone. Oh, last thing. And this is going to be, too bad. I already said I'd do something. In fall 21, when I made this video, we're getting Project 4 out to you before Thanksgiving break. Don't feel that you have to be coding during Thanksgiving dinner or you're behind. You can take a few days off. It's in the total number of days is planned around, like you should probably be coding up to Monday, maybe some on Tuesday. You should definitely be coding Sunday when you get back. But if you take off 4 or 5 days there in the middle, you'll still have enough time to do Project 4. Many people find Project 4 to be less work than Project 3, but a little bit harder to debug when you get these odd answers of, hey, my part C is spitting out wrong answers or taking too long. It might be a little harder to debug, but the amount of code is going to be potentially the shortest project you've written. Okay, so good luck with the project, everyone.